Okay, I think hopefully we're rolling. And there's some video. Okay. How is everybody doing today? Can you hear me all right? And I'm not sure I'm hearing anybody. Hello? Ah, that's better. Okay. I mistook the power on light for the charging light. Yeah, that's how these days go. How's everybody doing today? Good. That's good to hear. All right. I'm making it up as I go along. Sometimes it seems like you have to do that these days. Yeah, things are going pretty well. I'm trying to follow all the on-campus excitement. Not that there's too much excitement, I don't think, but trying to be ahead of the situation. I've been hearing about remote people needing to get COVID tests. Was the new news flash to me. Have you heard about that? Any of you who are being remote, have you been contacted? It's my public service announcement for the day. Sure. Right. Right. Yeah, it is. It is. It's a tough call. Yeah. When I first heard that, I pretty much had that exact reaction. I guess there's a lot of people are, concerned. People from outside, parents and whatnot, just want to, they want to make sure that their students are safe, whether they're on campus or not, and that sort of thing. And I guess there's a feeling that there's potentially some circulation among people who are on and off campus, or remote and not remote, I guess, is more the concern. Yeah, it's, I don't know what to say other than that, but in case you hadn't gotten I hope I'm not being the bringer of bad news for those of you who might not have heard that, but it sounds like campus has already reached out and got a hold of you on that one. But in the meantime, overall, my understanding is that the campus is doing quite well with regards to actually keeping the instances of COVID down on campus. So good on all of you who are helping keep that down. So I thank you so much on behalf of the greater Rensselaer community. But that's not about computer graphics, I suppose, but that's the public service announcement part of the day. Let's see here. So over in the, let's see, what do we got here? Over in the general channel, you may have seen that I am kind of working out some things with regards to the check-ins and project and homework submissions and so on. I think the check-ins are going well. We're going to continue those. I think they serve a great purpose, just to make sure that people are kind of following along and everything is going well. But out of an abundance of fairness and in terms of when things are due and to make things more predictable and so on, to go ahead and take that extra step and somehow kind of formalize the submission process a little bit. That doesn't mean, hopefully what you may be a little bit out of sync with regards to the check-ins, but everybody will be in sync with regards to the submissions. So I'm going to try to get in and be grading it on top of things to kind of nip any issues in the bud by trying to, look at all the submissions as they happen. So according to the, straight schedule. But I may not get to talk, through things personally, until later after that, just because of the limits of time and space. But it'll work out. It looks like we're split about 50-50 with regards to people who are comfortable with Git and not so comfortable with Git or want to do an LMS, just a straight up LMS submission. The LMS submission makes life a little bit easier in general because that's where I can just post a grade. So that's the one bonus of that. So I think I'm going to kind of standardize on the LMS version where as it mentioned in the syllabus, submit your C++ files, your H files, any PNGs or other textures that you need for your program. And hopefully, if all goes well and everybody is using Windows 10 and we're on 64-bit operating system and whatnot, and everyone statically links their libraries, fingers crossed, maybe submitting an executable will work and make life simple. We'll see how that goes. If you are using Git, though, that is I would love to say you have extra credit for that. I would suggest everyone do it at some point. If you're not comfortable with it now, at some point become comfortable with it, because the use of source code management and versioning is just a really great resource for you to have. And I'm happy to kind of look in and kind of see, and so if you have issues and I can grab your repo from there, that's really cool that we can kind of stay in touch and kind of coordinate and evaluate work on a more continuing basis using Git as well. So I'm going to encourage that, but not require it. But I will require the submissions on LMS, just so everybody's sort of on the same page. We'll work that out. What I have done, I know everybody's probably wondering right now, well, what about this last project that we had? What about any homeworks and so on? So for now, we're going to, we'll take care of sharing repos in just a little bit offline, I guess. But where was I? LMS submissions. Oh, yes, trying to come back up to speed. So for now, I have posted a submission point for Project 1 and put a due date of Monday night. So just since it is a change, I wanted to give everybody a chance. Hopefully your Project 1 should already have been done, but this one time you won. We have to have a submission by Monday night. Plenty of time. Again, the idea is basically to show, yes, you've got Visual Studio up and running, you have your libraries installed, you've got the basics down, you're able to compile, kind of the basic stuff, so that we know you're not going to get lost as we go, onward and so on. I have started a post in the Project Ideas channel over on Discord, a bunch of, sort of things that I think would be certainly appropriate for various parts. Some of them are maybe a little bit more towards final project sort of stuff. Animating a Rubik's Cube, if you want to include a Rubik's Cube solver, that'd be extra credit. But, animated cubes using textures, using the techniques that we're showing in class, not just, flat shaded polygon kind of stuff, really kind of going steps further, possibly getting into skinned animations and things like that. But you'll see lots of, I'm just going to keep kind of posting brainstorming ideas in case, you're looking for an idea to kind of spur you along, to kind of, get the creative juices flowing as to what, what I'd be looking for overall in projects. Now let's see, I have to open up my seltzer here without spraying it all over my desk. Sorry. Any questions on that? I'm sure there will be as time goes on. But for now, just think of it as inspiration. And any questions on either the homework submissions or project ideas? So far, so good? All right. Okay, so for today, what I wanted to do, since we are I think we are still officially in week 3, we're actually in pretty good shape with regards to getting, chapters behind us and starting again to really kind of the meat of OpenGL and some of the graphics things that, real-time 3D graphics that is going to be particularly of interest in game development and kind of real-time simulations and so on. So we're doing pretty well. I've been trying to find some more resources. I've been posting them in the resource directory as well. And sometimes, like I mentioned in the resource directory, if it seems like I'm posting, 6 different ways to skin a cat with regards to these particular chapters, it is because, this is really kind of fundamental, foundational kind of stuff. It's not it's not particularly complex, but it is, you kind of have to go through it. Once you go through it and you kind of get the gist of it, then it starts to make sense, and hopefully you won't be lost as we keep adding and adding and adding to it. So today, to kind of wrap up some of the math, or to wrap up the math stuff where we were at, the foundations, and also kind of look forward sort of a little bit into chapter 4 and the proper use of shaders, more reading shaders from the from separate files, and also loading geometry from buffers and so on. I'm going to look a little bit forward to some of the to some of the chapter 4 stuff. But as far as materials go, I really am hoping I'm going to go through this other, because I think this is a pretty good example to kind of once again drill in these ideas behind the use of matrices and what they're for. Now this is posted. This is the OpenGL tutorial.org, their tutorial 3 matrices, and it's a really good example. I thought this was kind of spot on, even better than some of the explanation in the book as to why you're using things. The first bunch, again, hopefully is fairly obvious to those of you who have had the basics of matrix and linear algebra and why transformation matrices work sort of the way they do. Which pairs of numbers or triplets of numbers they're sort of acting on, depending on if you're doing something like rotating around z or scaling in a single dimension in y, or and so on, how they can work together and how you can potentially concatenate them or add them together to one another. So the first part, I don't think necessitates an awful lot more discussion. I think that part is going to be straightforward. What now starts to get interesting, and this is really becoming part, they've kind of mixed in what we're going to start seeing in chapter 4, which is, okay, now how do we use the OpenGL and specifically our GL math libraries, GLM, to kind of do the sorts of things that we want to do. Okay, so if we're looking at the example that they have, they're showing some pretty straightforward, what does matrix multiplication look like? What does a transformed vector, if you have a transformed vector, what is that? You're basically taking a matrix, multiplying it by a vector, and you will get back a transformed vector. Okay, if it gets scaled, if it gets rotated, if it gets translated, you're taking a transformation matrix, multiplying it by your vector. Order is important here, right? And you get back your transformed vector, right? Now you do want to start paying attention to the particular order because of the way things are assumed with regards to how OpenGL works and the way that order of operations work. So this is a good one once we get through. So first we're saying here, the first one here is the basic idea of matrix multiplication, okay, and what it looks like in your code. Yeah, pretty much the same, pretty much as it should. And then we have translation, which is adding our X, Y, and Z offset. And then they introduce the identity matrix. We have scaling matrices, rotations, and we accumulate those transformations as we go on. Now, some things to call out, worth mentioning. Specifically, about the order of operations. Now, it's not the order of operations with regards to the math itself, but sometimes when you are thinking about how you're manipulating an object in space, the order of operations is going to be important, right? Because if you do a scaling first, the assumption is a scale is done around the whatever happens to be the origin at that moment, right? So that may be kind of a different effect than, say, a translation first and then a scale, right? Because the origin will change, right? There's a little bit of kind of the precedence of things to kind of keep track in your head, right? So, for example, in this line here, they show a demonstration of saying, okay, well, we're going to say the translation matrix times the rotation matrix times the scale matrix times the original vector. So what's really happening here, this line actually performs the scaling first, then the rotation, and then the translation, right? This is how you want things to happen, right? So if you did things in different orders, it doesn't produce the same results. So you can accumulate them, but you have to be careful about how they associate. The associative properties kind of can potentially break things down. And they have a good example here. So saying that the order of operations, you need to be careful specifically if you have game characters or objects or ships and so on. So imagine this, okay? Generally, you want to scale first, then change the direction, then translate, right? So for example, if you had a ship model, the wrong way to do it would be to move first, to translate it, and then scale. Why would that be? Well, remember what I said the other day. If you are scaling, what a scaling is, a pure scale, is moving things away from the origin, right? You're multiplying in each dimension, moving them away from the origin, right? So if you move your object away from the origin first, then the points, the vertices of that object are going to move away, not from the center of, potentially away from the center of the model, but from the center of, wherever the origin was, right? So that's why you sort of have to be careful, right? Here's the first thing. So they say, okay, translating a ship to x10, 0, 0. Now the center of the ship is 10 units away from the origin, but then you scale, scaling the coordinates to relative to the origin, and that's far away from it. So the scaling is going to happen in kind of a weird way. Everything's going to be pushed out in this kind of weird perspective that you probably don't want. Let's see. Sorry, I keep smacking my microphone here. So you end up with a big ship, but the scaling was centered at that which you don't want. So the right way to do it, to do a pure scale and then a move, is to scale first. So scaling with the center of the object where you think it should be. All right, that's why it's important to kind of maintain what the center of an object is when you're scaling it. So scale it, you get your bigger ship, centered around the origin, and then move it. Now sometimes that might mean if you wanted to scale the hand of a model, you might have to do things like move things around, scale things, move things back again. So you don't be too surprised if sometimes in your code, as you get even more complicated, you're doing these kind of extra scales and rotations and movements to kind of get things to look exactly how you want them to, which can be a little bit odd, but be aware of that as you run things. We're not going to get too much into that. Perhaps in your projects you might need to, but be aware of that. Okay. So this is why we're going to kind of, you're going to see these kind of standards set for it here. All right. So next, we talked about this before, and one subtle thing, and they brought this out in this one as well, that I really liked their mention of this, is this notion of the model, view, and projection matrices. We talked about them on Tuesday as well. And the idea that the model view is the orientation of the model in the world, right? We got that one, the where the model is in the world. The view, which is, and here's where it gets tricky. And this, I think I probably could have been more clear the other day, is that the view is gonna represent that relationship between the world and the camera. But, and here's the big but, that you're not really moving the camera, right? This is the view. That's why we don't call it the camera transformation. It's the view transformation, because ultimately what's really happening is you're applying a transformation, a second transformation, to the object that you're going to transform as if it were oriented according to the camera, right? There is no camera. So if anyone's been asking themselves, gee, where is the camera in OpenGL? So far, we haven't really dealt with anything like a camera. If you look at any of the code, there is no camera, right? It's really this it's the combination of the effect of the projection or perspective matrix and how the negative of what would have been the camera, how they're applied to the model. And there's a great quote in here, which I guess is from Futurama, which I just thought was the greatest quote. The engines don't move the ship at all. The ship stays where it is, and the engines move the universe around it. Right? So imagine you want to get to the world, and you're sitting in your ship, or you're getting somewhere out in space, and the ship stands still, but space around you moves to accommodate the ship. Now, that's not exactly what's going on in the case of OpenGL, because the universe sort of moves with you. But the camera, it's sort of, you're shifting everything around the camera as opposed to the camera around everything, right? Because there's a fixed point of view that's sort of at, which is why we have these matrices being applied to the vertices of our objects and not just some simple manipulation of a camera, right? And they do a pretty good job of this. So we have the view matrix. Let's see, let's go through again. Okay, somebody's typing. So I was going to ask, are we following? Whoops. So does that mean we have to do all our transformations and stuff backwards? No, it's just the view matrix that's sort of the opposite of what the camera would be. It's not really backwards. It's backwards as if it was what the camera would have been doing, right? That's the only one that's really negative, right? And normally the view matrix is the one that's done after the model transformation, right? So some of it is taken care of, sort of automatically by the order that we do things in, but it's important when you are creating that view matrix to keep that in mind, right? That it's not the camera that you're moving, it's sort of the equivalent motion of the world around the camera. Right, yeah, that's it. I wasn't saying the object moving. I should have said it wasn't the object moving, it's the camera. So everything is being moved around the camera, right? It's being transformed, translated first in its model space and then in the world space around it. Right. Okay, so in the case of, here we have, I was going to say Joanne, but it's not Joanne. Suzanne the monkey from Blender. If you're familiar with Blender, you probably have seen Suzanne the monkey. Everybody has to have their pet mesh that they use in their 3D programs. Blender has Suzanne here. So once again, the model matrix is the geometry of the model, the vertices, the triangulation, everything of the model within its own space. So you see, I want to say Joanne now. Suzanne here is centered, this is the center of that model. All of the other vertices are with relationship to that particular center, right? So because of that, if you just right at that moment scale, it scales appropriately. It does the right thing, right? It just grows that object around its center. Everything will be uniform and wonderful, right? If you rotate it, it rotates around that center. It doesn't orbit, right? If you translate it and then rotate it, well, then it's going to be potentially a little bit odd. So that's why we do these things in this order. Okay. So if you want to move the model, you can do that. And now, if you are moving the model, you are moving it in world space, right? So now, by moving away from this, you're saying, okay, it's as if the origin were here, but now we're moving the model away from the center of the world. And you can even rotate it according to that. Right, so here's the combination. We have model coordinates and world coordinates. And then here's our Futurama piece, right? The engines don't move around the ship stays where it is, and the engines move the universe around it. So now we have our camera, and if you view the mountain from, okay, this is another good example, right? So if you are moving closer, you have a mountain in the distance and you want to zoom in on it, or you want to, see it closer up. Yeah, sure, you can move the camera or you can move the mountain, right? You move the objects towards the camera or you can move the camera towards the objects. It's just a matter of which direction. So it's the opposite direction, right? So they mention here, initially the camera is at the origin of the world space. In order to move the world, you simply introduce another matrix that affects the models in the world, right? So to move the camera 3 units to the right, what you actually do is you move everything in the world to the left. I like that one. All right. So now we have our combination of our matrices, our world, and then, so here's Suzanne moving. Suzanne has the model view, then the world view, and then the camera view here, right? So we have 0 transformation, then we have the world transformation, then the view transformation, right? And there is a wonderful look at function that will help you along the way if you want. We'll get to that. So here we are. Now, next and finally, we have the projection matrix, sometimes referred to as the perspective matrix, once again. And this is an important part where it's not so much about changing the position of the camera in the world, but applying the rules of perspective, right? We're used to taking in the world where, for example, if we have a basketball that we hold right in front of us, it seems very big. If we hold that same basketball 100 feet back, it seems very small. The object hasn't changed its size, obviously, but the rules, the laws of perspective makes it look smaller. So as z increases, x and y decrease, right? We have that scaling that occurs, right? So it's the perspective of the camera, this last perspective transformation, that allows us to do a perspective correction on things. So the world, so it looks appropriately three-dimensional and not just being all flat orthogonally projected on our view plane. All right. So there we are, and they have some really good examples here. And this is the one thing I wanted to stress and talk about these, kind of demonstrate. If you're not careful and you look at what they're doing here, it's easy to get a little bit backwards. So I wanted to kind of step through it with everybody as we talk about the effects of perspective, just in case. Okay. So imagine you have your scene now. You have these set of 16 boxes, 16 cubes that you want to have in your world. Notice I don't say in your scene or in your view. They're in your world. They may be in your view, but that's going to depend on where you want to position your camera and also what happens with regards to perspective. Okay. So where I'm pointing with my mouse, hopefully you can see that, right here, or actually somewhere back here, is the origin from the camera's perspective, right? The camera projects this frustum, this sort of cone or pyramid of what it is going to see according to its perspective, right? Start at a certain point, and it works out according to, you know, the field of view, and maybe if you want to get into the physics and simulations of the lens on that camera. But generally, we have a straightforward, kind of a simple field of view, an aspect ratio, and ultimately what we're seeing in this, we're seeing a clipping plane, 2 clipping planes, one here close to the camera, the near clipping plane, and the other one at the back of the frustum, which is the far clipping plane. So anything that intersects that frustum is what we're interested in actually rendering and seeing. All right. Now, the perspective correction is what gives the viewing area its characteristic shape here, right? Things in the front, if you did a slice and said, okay, between 0 and 1, right? If we said between 0 and 1 here, but this is also 0 and 1, right? That's the mind-blowing part. Things that here obviously are occupying more of that field than things that are between here, 0 and 1. So to get these things to appear as they should be, we have to take their geometry and scale it down, right? That should hopefully make sense. So what's ultimately happening, now, we're not really, again, we're not changing, we're not actually creating optics of a camera in this case. What we're doing is, once again, we're modifying the behavior of the world, right? We can move the world around. We can also apply certain types of transformations to it based on the relationship between the objects in the world and the camera. And that's what that perspective or projection matrix is doing. Essentially, this is a great image. I love this image. Now, this is the tricky part that when I first saw it, I was a little annoyed. So right now we are here. This is where we're standing. We're viewing this, I believe, from here, which is why we see these things should be close up to us. They occupy more of the field of view. And then as the depth away from us increases, these things each occupy less, right? So in the corrected world, we actually are back to this cube. We have a cube that we are really looking at, and what we're doing is we are scaling the things in our world. We are applying these transformations to the objects in the world. We're not transforming the camera. We're not changing, the images once they've been rendered. We are actively, using a transformation on the vertices that we're creating. So that's what's happening. So if we were able to kind of, extract ourselves from the scene and view it outside, in this case, the camera really is somewhere sort of in three-dimensional space where I'm kind of pointing my mouse here, right? So we're viewing it from this way. Now you can see that, all right, what we're doing is we're scaling up these objects because they are close to that plane, and we are shrinking these objects because they are further away from that plane, right? So this back here, this plane is actually the far clipping plane. Whoops. The plane that's at the back of the frustrum here. And this near clipping plane is actually the one that is over here, which is why we see just parts of these two cubes distorted appropriately. And then we would see, actually, if they weren't occluded by these first two cubes, you would see more of these cubes in the distance, right? So this is what it looks like. So we actually are looking at a cube, but everything in the cube has been scaled to reflect that transformation. Mind blown yet? That needs a poll, I think. Either that or everyone's just like, we've got this. So humor me. All right. They say in here, you should read this one 8 times, and then it makes perfect sense on the 8th time through. Okay. So this is ultimately, and in the end, the nice thing about it is, as mind-blowing as all this is we really build our transformation matrices one at a time in ways that make perfect sense. Then we add them, we accumulate them together, we multiply them by our objects or by our vertices even, and it just does the right thing, right? As long as we can remember why they're done in this order and be careful about your manipulations, right? So as you are manipulating your transformation matrices, you're putting them together, and it's going to get a little crazier as you start moving models around and have different pieces and parts, but you'll get there. All right. So this is a good example. Then it puts it all together and shows, ultimately here's our what would have been a normal triangle, but now it's scaled according to how it was in the world. This group of tutorials is actually pretty good, and it matches up nicely with what we're doing because it is using GLM. I believe it's using GLFW as well, was it? I think they're using it in their series. So if you need additional sort of stuff, you can certainly feel free to jump into here. Let's see. Trying to find their setup here. Anyway, so this is a good set. Some people have been asking about, is there the one thing the book doesn't have a simple translation between, like, okay, single triangle. Suddenly in chapter 4, it immediately jumps into cubes, just to kind of blow your minds. This one has a pretty good example also of, just a triangle, but the right way, okay? The book sort of did the triangle in the brute force kind of wrong way, in which you kind of hard-coded our triangle coordinates into, now let's see, I'm also going to check. 1 o'clock. Where am I? Okay, still got some time. 1:20 is when I'm supposed to start. Yes, okay, so still a little bit of time. All right. So we jumped right from our kind of brain-dead, hard-coded triangles in our shaders over to cubes that are done using vertex buffers. Now, if that's a bit much, and kind of look back at these, it breaks it down the same way. The first triangle creates a vertex array object, which is our overall context for how we're going to be working. They go ahead and wonderfully said, okay, we're going to say that there are 3 vertices, and this is their vertex buffer, right? 3 vertices in a vertex buffer. In order to draw it, okay, they generate a buffer. They ask for 1 buffer. They bind that buffer saying, okay, this is the buffer we're using. Then GL buffer data, that moves our buffer data, which is this here, G vertex buffer data. As you saw up here, G vertex buffer data. So it takes it from the CPU, tells it what its size is, and that's its size in bytes, so that's size of. That's going to say, okay, all of that winds up being, if it's floats, each one of them is 4. Whoops. So we have 4 times 3 times 3. All right, so we have, what should be what? That's 36 bytes off the top of my head, size of. And it's going to move that buffer. It's going to say, okay, OpenGL drivers, take it away. Now they're yours. Right. And then, of course, we can't forget, we have to describe the contents of that vertex buffer to OpenGL. And that's where we use our attribute array. Okay. We start off, we enable the first or the 0th attribute array. We tell it, okay, this is the buffer we're using. And here is our attribute pointer. So it is attribute 0. Each one has 3 parts in its vector. They are floats. It doesn't need to be normalized. And in this case, this is a special case. Since we're only dealing with a single attribute, we only have vertices, they can get away without specifying the stride. They don't have to worry about how to get to the next vertex where you have kind of multiple attributes for it. So this is they kind of cheat on these two sort of things. All right. Then they go off and they say, okay, GL draw arrays, GL triangles, and they draw those 3 vertices as triangles. Then you disable the vertex attribute array, good practice, just so that, you know, if you do then have a model that you want to then do different things with it. They show their shaders. Shaders are pretty straightforward, you know, similarly to ours. Go through the book. Some people have been still having some issues with regards to shaders and, you know, forgetting line ends or, you know, just kind of getting some code messed up. That's why it's super important to include this stuff. The book gives it a good example of all of the error checking for the link, the compile and link process of the shaders itself. Do that. Don't leave those parts out, right? So let me show what happens in those circumstances. So for example, let's jump back over to a code, and I'm going to look at here, I'll show a little bit. This is actually exercise, or sorry, not exercise, but the example 2, which is not the plain red cube, but an interpolated color cube. And in it, ultimately, I think if I've left it set up correctly, here's what's happening, and I'll drag. It's not my default monitor over here, so hopefully. Okay, it is not working, but there's a reason for that. So if we look, we get a blank window. We've got nothing in the window, But I can go over here and see, look at this. Linking failed. Programming info log vertex info. Error. Undefined variable ASDFGG. Incompatible options for link. Okay. This will save you a lot of embarrassment and problems if you use the error checking, right? I had left a bug in here, and I guess I didn't move the new shader in. I've now since fixed it. I think okay. Yeah, fixed it in here. And now if I stop and I tell it, okay, rebuild all. Now, depending on how you have your workspace set up, and let me talk about that for just a moment. Actually, make sure this works first. That's kind of a weird thing. I'm going to run it now. And sure enough, if I look over at the other screen, and I'm getting a red cube again, even though this is the interpolated color or the varying color version. But I'm just still getting a red cube because I've set it up that way, so we can talk about the red cube. All right. So make sure that you have implemented the error handling for the OpenGL shader stuff, especially. Super, super important. All right. Any questions on any of that? We're kind of at a good point here. We've kind of stepped through now. The simplest triangle version is just 3. We're going to get into drawing cubes now. And you'll notice this cube there we go. Anyone already looked ahead at chapter 4? Of course not. You've got better things to worry about. You're flooded with your other courses. All right, so I'll tease you with this one. I'm actually going to tease chapters 4 and 5 because 4 and 5, this is, like I said, this is kind of, we're now the meat and potatoes of OpenGL. Okay. In it now we are going to be drawing objects. We're going to be using our math to locate things in space. We have proper shaders. We're going to use more than just positions. And in chapter 5, we're going to be even adding texturing. Okay, so let me even jump ahead just to tease you with chapter 5 even. So an example of where we're heading. All right, I'm going to pull the other. Okay. So once upon a time, this is basically about all we had. We had, okay, let's get some polygons and let's get some textures. Now you notice this one, I've gone one step further and I actually even have these little arrows pointing to the top of the texture. What I'm doing here is I'm animating the texture. And how I'm doing that is I'm basically flipping what texture is used. So one of the reasons I wanted to talk about that and show that as an example is some people have also been asking, well, it looks like there's a bunch of kind of redundant code in some of the examples. You know, like why is it always adding the using, telling you, okay, use this program, or use this context, or use this buffer, and so on. It seems like nothing's changed. The state hasn't changed. Why do we keep saying it over and over again? And that's because ultimately those are the things that we're going to be able to change on a frame-by-frame basis, and even within a frame to change certain things about what we're rendering. If we're rendering multiple models, if we have to do things like move one model or one object in the scene separately from the other. So a lot of the examples right now, they're written in such a way that what seems to be redundant are hopefully just going to make life easier as we add more complexity to them, so that you're not going to forget that, oh, I forgot to bind that buffer, because then you switch to another buffer, you did a different thing. Like here I'm using 2 different textures. I don't change much, I only change the textures in between, right? So some things can be preserved, some things have to be changed in that loop. So for those of you who have asked questions about that one, that's one of the reasons that's there. So I'm going to come back to section 4, and this is one concept I want to make sure, and then we'll stop and I will do, well, no, I guess a little bit more time. we're okay. All right, I was worried about time. So go back to what was the other example for section 4. Now you'll notice the first thing it's going to ask you to do is, of course, draw a red cube. And in that code, now it's introducing this idea that, yes, we are dealing with vertex positions once again. Right? We have vertex positions. We're not hard coding things into our shaders. If you look at the shaders going forward, let's see. This one's a little bit more complicated because of the varying color part. You can ignore the varying color bit here. Ignore that for just a moment. And the important part is this piece here, in that now we are getting the position from the buffer, and that's the position of the vertex that we can then use, that we can then decide, okay, that vertex position needs to be transformed, translated, perspective, kind of corrected, right? We're not doing that if this one, if the first one do this, the first one, second one do that, the third one do that, and so on, right? So now the shaders themselves are a little bit simpler in terms of, not hard coding numbers in, but we're going to be getting into the actual use of matrices here and the multiplications. Now, it starts to also get into a thing where you're going to think, okay, is this the absolutely positively right way to do stuff in terms of, especially with regards to the model view and projection matrices? Should you just glom them all together, and should that just be one matrix that you then just multiply everything by once and it just goes away? Well, it's going to depend, because sometimes you're going to have a different world transformation if you have multiple objects in your scene. If you're, depending on how you are potentially maybe animating an object, does it make sense? Are you doing operations that are different for each and every one of the vertices? So if it's different for each vertex, then you wind up doing it in the shader. If it's once for the whole model, maybe you do that calculation down in the CPU level, right? So sometimes you're going to start to see a little bit of variation in where this projection matrix and the model view matrix, when they sort of get catenated together, right? So in this next chapter, you're going to see that they've pre-cooked the model and view matrix together, and then do the projection as part of the vertex shader. That's one way to do it. You could cook it ahead of time if you wanted. Or you could keep all three separate if you wanted. So we start to diverge from you have to do it this way sort of thing. Now, so that's the vertex shader, is really just, grabbing a position and applying the transformations to it. The fragment shader in this one also, now, if you look at the first example where we just say, okay, there's just a set color, and it might have been red. So if we look in the previous fragment shaders, like even in this one here, this says, okay, here's color it red. And your shaders that you've done so far have been that sort of shader. Now, this shader in 4.1.2 is going to introduce this idea. Some people have also asked, can different shaders, can vertex shaders and fragment shaders, how do they talk to one another? Well, there's a few main things that they do. You can have, like in this case, our vertex shader has an out. You'll see that there is an out vector 4 called varying color. Right? So this vertex shader actually does have an output that's going to get passed down to the pipeline. Right? And the cool thing about that, let's see. Now, first off, you can say, okay, well, here's varying color, and I just set varying color to red. Vec4 1001, right? Red, fully opaque. And so that's why in my case, when my program runs right now with this particular vertex shader and this particular shader, I'm passing that red color in through varying color. See here it says in vec4 varying color. And then my main doesn't really do anything with regards to color. Eventually you could have colors for each vertex if you wanted. But in this case, they're all either red or going to be some calculated value. So I'm passing it solid red, and I run. Hopefully, make sure to choose that one. And I'm going to say rebuild just in case. And I can only mention, I got to keep mentioning this over and over again. Also, it's up to you, however you want to implement things in your Visual Studio project to make sure that when the actual executable gets run, that the shaders are in that same executable directory. Okay, because that's where it's going to look for them. It's going to as the same, either the working directory that the debugger sets up or the executable directory where the executable wound up. Right? If you're debugging, it winds up in the debug directory. That's where you want it to be, or in the executable directory. You can kind of work with Visual Studio to do the right thing. But anyway, so I have a red cube because I set varying color to be red, and then I passed it through this varying color. And I don't think the book does a particularly good job of explaining what happens next. So I want to mention this. Okay. As you read chapter 4, if you want to get ahead, you'll say, okay, well, now what it's going to do is it's going to say, okay, I'm going to come up with a varying color according to the position of the vector, the position of this vertex, and then some other amount. I'm going to add a little bit to it so that it's going to wind up not being too dark. It's going to be at least half tone, or half red, or half, brightness. Bring the brightness up. Okay. So now I'm going to assign a varying color. So this is being called once per vertex, and it's going to calculate this thing varying color once per vertex, and it's going to pass varying color over here to our fragment shader, right? So any intuition as to what's going to happen? What are the colors of the faces going to be? If each vertex has a color calculated for it, how is OpenGL going to decide what color to make it? I'll let some other, it's always good when the first answer is the right one. I gave it away. So it is a gradient. It's actually interpolated. It does wind up being a gradient, sort of interpolated between the two. So again, if you've never encountered OpenGL before, and I've broken this one also to make it do the wrong thing for us here. But you can see each vertex has a color, and then in between, it's going to interpolate in between those colors. All right. So why is that happening? So the interesting thing you might be saying is, well, okay, the way the vertex shader, it's going to be called once for each vertex. But then the fragments get called over and over and over again. So how do we get all these in-between values? And the answer is any vector or any value that's passed between the vertex shader and the fragment shader is going to be interpolated. It's actually going to be constantly changed according there. There's some ways we can change the mode in there, but automatically, as part of the pipeline, it's automatically going to interpolate depending on the relationship of the vertices in that polygon. Right? So it's going to take an average of, it's going to use basically, imagine you had the center of the polygon, or wherever you are on the polygon, it's going to say, okay, this particular fragment that I'm asking you to draw, it has already ahead of time interpolated a number for you based on the fact that you're in a triangle that has 3 vertices. How cool is that? Isn't that handy, right? Makes life much, much easier then trying to figure out, okay, what's going on. And this is particularly good because of like shading and color and so on, so we can kind of fill in. And that's also very important when it comes to texturing, because obviously if you're trying to texture a triangle or texture something, you're going to have to, where on that polygon are you, and how do you weight things and so on, right? So that's an important thing to know, and I don't know if it even said it explicitly, and it doesn't get said explicitly enough. You just figure it out. That's what it's doing in the normal case when you're passing things from a vertex shader to a fragment shader, is that you have that implicit interpolation going on. You can control that. You can actually say, oh, okay, so normally it's using smooth interpolation across, and there's a way to set the interpolation value. I used to remember it off the top of my head. There's smooth, and we'll get there. Okay, I'll finish up with one last thing. Now, last thing I want to show before doing check-ins is also this bit that they sort of introduce and don't talk an awful lot about. But actually in chapter 2, this was mentioned, but it's easy to kind of just jump over this section if you're not sure, because they talk about the depth buffer. And there's a bit of kind of pseudocode in there explaining the depth buffer, but you never actually implemented the depth buffer, because this is another thing that OpenGL does for you, right? As you're drawing fragments, it's actually behind the scenes, it knows, okay, you drew a color, and it knows the geometry of that depth, or potentially knows the geometry of that pixel, the depth of it with regards to the scene. And it can decide, does that fragment get colored according to, imagine things move around, or have models have, like in this case here, we've got some, the bottom and the front are two different sets of triangles. How does it decide which one to draw, which one actually gets to the screen? Now here I've turned off the depth buffer, and so it's like whoever happens to get drawn in whatever order. So that's why it looks weird. Like we can kind of see inside the box here, as opposed to seeing the a solid box. We can kind of see inside. That's because I've broken the depth buffer on here. Not really broken. I just turned it off, right? So in chapter 2, they mention this depth buffer, and the idea is as you're rendering, as the fragment shader is cranking away, it knows what color you're assigning to that particular point in the world, and then it just compares to a depth buffer and says, okay, the pixel that you just drew, is it closer to the camera, or closer to the clipping plane, the actual projected plane? Is that closer to that than whatever's already in the buffer? And if it's closer, it says, okay, I better draw it, because that's in the way. It occludes whatever's behind it in the world, right? When we were looking at the perspective matrices and the transformations, we kind of got into that a little bit, how things that are closer to us occluded stuff in the background. Now in our simple approach, it's just using a simple depth buffer, and it actually does draw stuff in the background, and eventually it will draw, the closest thing is the one that winds up on the screen because of this depth buffer. So if you're looking at this code and you're saying, well, what are these few lines of code? And I'll just draw your attention to them here. Main CPP, you will see GL enable depth test, and tell it that the depth function to use is less than or equal to, right? So if the depth is less than or equal to whatever's the most recent one, if it's the same, it's going to get colored. Now, if I run that, you'll see that that is going to hopefully do the right thing now with just one simple change. Now I have what looks like a solid cube. And I better get to checking in with people. If you have any questions, go ahead and post in the chat. One other thing I wanted to, as a challenge, extra challenge to any of you out there, and it's not particularly complicated, but there's we'll talk about it on Tuesday, is how would you properly draw the cube as a wireframe? And think of a couple of different ways to do it. So there's one really, really easy one now in newer versions of OpenGL, but used to not be as simple as that, or they had to be some other ways. And let's talk about wireframes and why they are the way they are. Okay. In that case, I believe as far as the RCS IDs, I have Vesha, Dom, Favada, MASTRL2, Lin H8, and Young J14. All right, so I'll be checking in with you just to see how you're doing. And everybody else, make sure to get your Project 1 stuff kind of tied up and put a bow on it and put it in, submit it over on LMS. And have a great weekend. And feel free to send messages on Discord anytime. Okay? All right, we'll jump out of here now.